Classifications of DC machines, and after completing this topic I will explain some basic characteristics related with DC machines. You know, electrical machines are devices converting energy by using electromagnetic medium. So classification is based on how we produce magnetic field. DC machine needs magnetic field to convert energy, and magnetic field will be produced in three different styles. One, using permanent magnets. Permanent magnet DC machine. Permanent magnet DC, let's say motor. Generally we use those kind of machines as motors. Permanent magnet DC motors. And remember, in DC machine construction was like this. Here's a pole and pole face on the stator. There are at least two poles, and here's rotor. Rotor is slotted, and armature winding is constructed on rotor. Here is commutator, segmented pieces, and then there are brushes touching the commutator, and we apply armature current here in motor application. We deliver some armature current to load in generator operation, but let's say that is motor, we apply voltage and current. Here are magnetic field producing poles, you know, poles, and all those poles are connected to each other via the part called yoke or body or frame. That is yoke or body. Sometimes we say body or frame. All those are okay. Magnetic field produced in poles, let's say M pole, and then that magnetic field comes up from M pole, passes through air gap, cuts armature conductor, makes energy conversion, and passes through air gap and completes its circuit. Always. As you see, we need magnetic field to produce electromotive force, to produce torque. Let's say torque is equal to blah blah, EMF is equal to blah blah as a function of magnetic field. Here you see. So the question, how we produce that magnetic field? Here it is. We can produce magnetic field by using permanent magnets. We can produce a magnetic field by using electromagnets. Electromagnets, I mean, here would be some coils, current carrying coils, and then those are connected series, and then here are field. Let me choose a correct current path. Yes, here it is. Let's say current is like this. Okay, we apply a DC power, and here's a field current, DC voltage field, DC voltage. Always we use DC in these machines. And here's field current. Field current produces electromagnetic field. such a current will generate a magnetic field like this. Use your right hand screw rule. That is the field direction. Magnetic field comes up from N pole, goes to S pole. So that is the current direction in the coil. Okay. In the second type construction, we have used electromagnet to produce magnetic field. Ta-ta! In this case, we have used a separate source to excite excitation current. Sometimes it's called as field current. Excitation uyarma in Turkish. Excitation current or field current, both are correct. To produce field current, we use separate source here in this case, and it is called as separately excited DC machine. Separately excited DC machine. It would be motor. Generally it is motor. You know, in the first course I said those kind of machines today are generally used as motor because producing DC is much more easier than what it was in the history. Today we use some semiconductor devices called as diodes, rectifier bridges, so we can easily convert AC into DC. There is no point in DC production. So we generally prefer synchronous machine to produce electric power today. But there are still motor usages, especially in mobile systems, in cellular phones, in automobile industry, in ships. We use DC machines, DC motors especially. There is another family, lots of different types are there. Self-excited. That current, field current, will be supplied somewhere. For example, assume that here are poles, and then on the poles here are some field coils connected series, and then here we have two terminals for field current. That is electromagnet, yes. We need to excite it. We need some DC field current to produce magnetic polarization. Let's say N and S. Here are the magnetic fields. How can we supply such a current? Someone can say, here is an armature. Let's say here is an armature, let's say motor operation. That symbol represents armature. And here is a excitation coil or winding. Those are the terminals, let's say C and D, let's say A and B. Those are the armature terminals. That is the shunt type machine. In this machine, that excitation coil can be directly connected to armature voltage. It can be connected parallel. Shunt means parallel. So, as you see, you have one source, let's say a battery here to supply terminal voltage, and then here is the load current, here is the armature current supplied via load current, and the load current will also supply field current. It is self-excited. It is self-excited. The same power coming from armature or coming to armature can supply field coil. In fact, it looks a bit nonsense, but assume that generator operation. In generator dynamo operation, here is the armature, Houston. To generate electric power, DC power, you need magnetic field, and you are on a island. There is nobody, no electricity, so you can produce electric power by using such a dynamo. Here's assume that wind turbine, and mechanical energy coming from wind turbine will be converted into DC electric power by using such a dynamo. Houston, you need magnetic field. Here's a field coil. That field coil, let's say C and D terminal labels, will be connected parallel to armature coils. In such a case, as you see, the armature current converted energy will also supply field current, and load current would be here. Here would be a load, and armature current, that is the Kirchhoff's current law, induced armature current will supply load current as well as field current. So, ladies and gentlemen, self-excitation. That is self-excited. But there are some requirements. Before, here is a field current. Let's say here is a RF field resistance. Before field current, there must be some terminal voltage here. Let's say VT plus and minus. VT over resistance of field winding will produce field current. Field current will produce magnetic field. Magnetic field produce electromotive force. Electromotive force cause some terminal voltage, and terminal voltage will produce field current. Ta-ta. As a positive sequence, everything increases each other. If there is an increasing current, there is an increasing field. That increasing field results in electromotive force. That electromotive force will increase terminal voltage and field current. That is a positive sequence, positive feedback. So it will increase up to a certain point. That process called as self-excitation. Self-excitation. We will talk deeply later. That is self-excitation process. First of all, to induce electromotive force, you need always magnetic field. In case there is no magnetic field, there will be no electromotive force. Magnetic field in soft materials, soft iron. Here is field current, here is magnetic field. Let's discuss magnetic field in a soft iron material. Initially it starts from the origin. When you increase field current, magnetic field in the poles will increase, and then it will saturate. That is the increasing part of the curve. Then let's start to decrease field current. It will drop in a different path. Such a curve, you remember, quote as the action behind this is hysteresis phenomenon. And even if there is no current in a soft magnetic material, here would be some remanence flux, Pr, remanence flux, remains in the some domains of the magnetic pole will be aligned. Some of them show some magnetization, even if there is no H. Remember that is in fact BH curve. It is identical. Even if there is no H, magnetic field intensity, here would be some remanence flux density, flux intensity and flux density. Here you see some flux density and flux due to remaining domains. Some of the magnetic domains will be aligned in the polarization. Now, as a sequence, first of all, here were residual or remanence flux. That remanence flux, when you rotate machine, electromotive force, remanence EMF will be induced. That EMF will result in a terminal voltage. You know, here's a equivalent circuit. Here's an equivalent circuit. Let me show you. Here's electromotive force plus and minus. Here is armature resistance. Here is terminal voltage. Behind the terminal voltage, here is load current, and here would be a load resistance. Okay, ladies and gentlemen, we can write Kirchhoff's voltage law around this loop. Induced EMF is equal to current times Ra plus Vt, terminal voltage. So, when you increase electromotive force, there will be an increase in terminal voltage and current as well, load current or armature current as well. And here is the, first of all, residual flux. It will induce a residual EMF. It will result in some voltage. That voltage will increase field current. Houston, take care. If there is a terminal voltage, there is a field current. That field current contribute residual flux. What I mean, here was a residual flux. Some domains were aligned priorly, and then here is an electromagnet. When there is an electromotive force, when there is a terminal voltage and field current, let's say such a field current will result in such a magnetic flux due to field current. Residual flux and field current will contribute each other. This guy will contribute the initial one. So resultant flux will be increased. The resultant flux will increase. Houston, resultant flux will increase electromotive force, will increase terminal voltage, will increase field current. Field current make much more contribution. It will increase field, and then it continues up to a certain point. That is called as self-excitation. I will turn back this topic again, but you understand that field current can be get by self-excitation. If here's a residual flux inside the armature or poles, then there will be some electromotive force, remanence electromotive force. That remanence electromotive force will cause some field current, and it will self-supply itself. Machine will be self-excited. And here are different type of self-excitation. One is shunt. We have already discussed right now. Shunt means parallel. And the other is series connected. Okay, let's discuss. That is shunt. Labels are C and D, A and B. And let's talk about series. In series connection, let's say motor, here's the armature, and then here's the field coil. Sometimes we show inductance like this, sometimes we show inductance like this. Here are A and B, and E and F. E and F. It depends. Excuse me. Let me change the sequence. E and F. Just custom. And here is the power source. Here's the power source. You apply some external power. This is motor. You apply terminal voltage plus and minus and load current. Here's the field current because that is a field coil, and here's the armature coil. Houston, all those three currents are equal: armature current, field current, and load current are equal in serial connection. Okay, that is the serial motor connection. The same currents will excite machine. That is also called as self-excited machine. Again, it would be a generator. Here is dynamo. Let's say we apply some mechanical input power via a wind turbine, for example. And then here is a series coil, excitation coil. That excitation coil will be connected series into armature, and then here are the terminals, and then behind the terminal, instead of power supply, here will be an electrical load because that is dynamo. In such a case, armature induces electromotive force and current. That current also supply field current. That current also supply load. Here you see, machine is self-excited. Field current is supplied via the induced power in the armature. Yes, there is a serial dynamo, but it is not convenient for electric usage. We use a serial connected dynamo in some special cases. For example, we want to make dynamic braking. Let me summarize here. Here's the same system in the box, the same system in the box, and here's a resistor called as dynamic braking resistor. It is out of topic today, but we just heat atmosphere here in this case. For example, here's a wind power, mechanical power, and then that power is consumed on this electrical device called as dynamic braking resistor, and then that resistors consume that power and system imbalance, so the mechanical part will supply electrical part. So in case it is in equilibrium, the mechanical system will be slow down because it is under braking right now due to such a resistor. For example, in case you have a lamp here, the power delivered to lamp is supplied by mechanical side. In case here are lots of lamps as a load, that power again will be supplied by mechanical power. They are in equilibrium. In case here is a dummy load means something in vain. Power on dummy load must be supplied by mechanical side, so mechanical side will slow down, so here is braking. Okay, there is series generator and motor, but for electric purposes, for supplying something, the series generator is not convenient to supply any high precision load. For example, here's a changing load. Changing load causes changing load current. It will cause changing field current, and when there's a change in field current, there is a flux change. When there's a flux change, there's electromotive force change. So output voltage, terminal voltage, is not stable in series connected generator, so it is not preferred. It is not very convenient. We never prefer a serial generator, but we use such a generator for dynamic braking purposes. For example, we are on a trolleybus. In fact, here you see a page, railway technology. Here are some resistors installed in the roof of the bus. It is not clear, in fact. Today there is no need to use, but up to 1970s there were some trolleys in Istanbul as well, and then there were some braking resistors on the roof of the bus. It looks like this, but it is difficult to find right now. There are some braking resistors, and because we use serial motor in a trolleybus, we use serial type DC motor in those buses. We use generation for braking purposes. And there are some resistors on the top of the buses. Here it would be those resistors are dummy loads heating the heating the atmosphere. It is not clear, but the resistors are here. Okay. Continue. There is no usage in serial generator. Only for special purpose we use serial generator. And those two are self-excited type machines. There is one more type, which is compound. Compound means bileşik. Combination of shunt and series, parallel and series. What does it mean? Let me show you. In shunt machine, take care please. I will complete something. Shunt field coil is designed for VT to operate at the terminal voltage. And then in serial type machine, serial field coil is designed for armature current or load current. All of them are equal. So here we prefer, in shunt machine, we prefer field current as low as possible, because it is directly consuming power from the terminal. But here it is something different. Consumed power supplied by a current, not a voltage. Supplied by a current. So it is designed for armature current. You know, to produce field you need MMF over reluctance. MMF is number of turns in field coil times field current. Field coil, current. And then, since armature current and load current is large, here armature current is large, there is no need to use high number of turns. Number of turns in this coil is small, but diameter of the conductors are large. Cross section are large. Diameter of the wires in the field coil, I mean, are large. What I said so far, here is a pole electromagnet. It would be self-excited. In shunt type coil, we design this coil and another one together with field coils. We design shunt coil thinner in diameter. I mean, cross-section area of the wires in the coil must be smaller. We prefer smaller field currents. It consumes electric power from the voltage. For example, the applied power here, terminal voltage times field current, is consumed on this resistance. Terminal power or voltage times field current makes copper loss in this field coil. So in case there is a very small field current, there will be very small amount of copper losses in field coil. That is shunt coil. Shunt would be connected to terminal voltage, let's say blah blah, and then here is a serial or series coil. Again, it is connected series with the other pole. Here is the serial terminals, ENF. Those were C and D shunt coils. Those are ENF, serial field terminals. They are thick in diameter, thicker in diameter with respect to shunt coil. They carry large armature current. They are designed for armature current or load current. So they are very large. To produce MMF, you know, the important is it is a product of number of turns and current. In case there is a high current, there is no need to use high number of turns. Here you see thicker conductors having small amount of number of turns. All those are constructed on a same pole, on the same pole. Such a machine is called as compound excitation. They are together. Shunt and series field coils are constructed in the same machine, installed in the same machine. Compound. Okay, the question, how those magnetic fields would be. For example, what about this current? Current must be in the same direction or reverse. If serial field coil contribute to shunt field winding, it is called as cumulative, increasing, contributes. Serial coil will make contribution to shunt coil. In case it is decreasing, in case serial field coil decreases the cumulative field, that is called as differential, because in differential phi serial, that is phi shunt, let's say, let me change color, that is phi shunt downward here. In differential type machine connection, these serial field will reduce the shunt field, will decrease the shunt field, reduce the shunt field. It's called as differential. If let me show you here again. Here is shunt field shunt downward, and then if serial field again, serial will contribute, increase the summation, cumulative, so that's called as cumulative compound, a cumulative compound, differential compound. There are two different connections. In fact, how can you do this? I will show you. Here it is. Here is the armature winding, here is the shunt field winding, and here is the series winding. Let's start from the beginning and repeat all the connections. Armature winding of separately excited machine, that is in old new literature F1 and F2, that's field coil. Let's say the machine would be motor, let's say motor, that is the motor current direction, armature current, motor. If the current is outgoing, that machine would be generator or dynamo. Okay, now here's in new literature armature 1, armature 2, and F1, F2. First terminals are generally referred as positive. That is a custom, not must. You can change, of course. That is F2, but as a custom we choose the first one as positive. Here's the positive terminal. In case it is drawing current, it is motoring. In case it is supplying some external circuits, it is dynamo. That is load current. Here, load current. Here would be armature current, incoming or outgoing. But here's always incoming field current, because without magnetic field there will be no energy conversion. Field current is always consumed, but that will be changed. That is shunt. In old literature we say A and B as a terminal label, and those are I and K in old literature. Old. Again, in old terminology, here's A and B, armature terminals. Here are C and D. In new terminology, those are identical, F1, F2. C and D. And in new terminology, here you see on the right hand side, serial field, series connected or serial connected machine, self-excited machine. The terminals, if you apply, let's say motoring, here is motor, the current is incoming, that is load current. Here you see armature current, here you see field current. All those three are equal, and then this side is positive terminal voltage and this side is positive, so we say serial 1, serial 2. Those are new terminology. In old terminology, here is A and B, here are two terminals, and E and F. E and F. Those are old labels. Here are three different major types. Here you see shunt series. Not 3, 2. Excuse me. 3. Okay. One is self-excited. Separately excited. 1, 2, 3. Here I have explained 3 different connection type. 1, 2, 3. Then you see compound connection. Compound, karmaşık, bileşik. In a compound machine, you see a shunt coil. You see shunt here. You see a series coil. Both are in the same machine. That is a special device. This machine is designed with 2 different excitation coil in one machine. In a single pole, you see, on a single pole, here are 2 different windings. One is ENF in old terminology. In new terminology, it is S1 and S2. That is C and D old terminology, and new terminology, it is field 1 and field 2. Those are the terminal labels. And those are in the same direction, you see. Fields of shunt, series field will contribute, increase the shunt field. So it is cumulative. Here it was cumulative. In case that is reversing, if this is reversing, and it is called as differential compound. You can manage, for example, let's say in cumulative, you connect S1 and S2 like this, like the above given. But if this part is connected to here and it is just crossed, just crossed the sequence S2 and S1, it is just opposite connection. In such a case, a series field coil will not contribute to shunt coil, and it is called as differential compound. There is one more thing. If the distance between armature and shunt field is short, it is called as short shunt. If the distance between armature and shunt field is long, that is long shunt. It brings out not a very complicated result, but to determine the connection, we use such a definition: long shunt, short shunt. If it is short shunt, the distance is short. If you cut it here and connect to here, it is long shunt. Please take care. Long shunt, short shunt. Here it is. Long, short. Both are possible. Whether they are cumulative or differential, it doesn't matter. Cumulative long shunt, cumulative short shunt, differential long shunt, differential short shunt, all are possible. It is the same machine, can be connected in both styles. The signs: incoming current represents motor, that is load current from the terminal, that's called as motor. If it is outgoing, the load current is generator direction, that is generator direction. Generator operation. Let's make connection. The field coils are open right now. Let's connect short cumulative compound. Short cumulative compound. Let's connect long. Here is directed to the terminal. That is long differential compound. The property cumulative or differential is important. Cumulative or differential, that property is important. But the long and shunt does not cause any dramatic change. It is not very important, but cumulative or differential connection is very important.